Hello everyone. In this video we are going to see how we can use the OpenFOAM's utility snappyHexMesh to create high quality mesh or a decent mesh without using any commercial software. Okay, so this is the model which I am going to use. This is a plane which I downloaded from the GrabCAD. I will give you the link for the geometry. So this file is in .stl format. Okay, and we are going to use snappyHexMesh to mesh this geometry. I mean a flow around this plane is the case. I'm not going to run the case, but we are just going to see how we can generate the mesh using snappyHexMesh. This process remains the same for any uh, geometry regardless of what it is. Like, it can be a car, it can be a plane, it can be a bike, or it can be a cylinder or square, anything. So the process remains the same and you can follow this. You can just replace the geometry and certain parameters related to the geometry as we proceed with generating the mesh. Okay, so this file which I have downloaded is in .stl format, but there is a problem in that. .stl comes in two versions. One is ASCII, the other is binary. Generally, when you download the model from any CAD modeling software as STL format, it will be mostly in binary format and not ASCII, because 3D printers can work well with binary with the STL file, but in case of CFD, especially OpenFOAM, you need ASCII format STL files. So to convert that, you can use FreeCAD, which is a free CAD modeling software, which I generally use for making CAD geometry for my CFD simulations. So I will load the STL file here, which is in binary format. So if you do not know what format it is in, whether it is binary or ASCII, then you can do the same and you don't have to worry whether it is already in binary or ASCII. You can just proceed with this and do this process, so it is mostly safe to do. I will go to mesh in this section, right click on aircraft and give export mesh. In export mesh, it will default be showing binary STL. So I'll choose ASCII STL, not ASCII STL.ast. It has to be .stl, and I will save it as aircraft ASCII. Okay, I will save this. Now we can close this. It is not needed anymore. Okay, so now I will delete this. I will open the file which we just created, which is aircraft ASCII. Now we have the file, right? But there is a problem again. If you see, when I turn on the data access grid, the scale is very high. If you work with OpenFOAM, you know that all the units here are in meters. So which says this length of the plane is around 40,000 meters, which is not realistic. It happens because when you export any STL file from a CAD model software, it takes the dimension but replaces the unit to meters. Probably this was designed in millimeters, but then it was changed to STL and it assumed all the millimeter values are in meters, which is not realistic, right? So what we are going to do is we are going to scale this down and with a factor of about 1000, so we are getting it in meters instead of having it in millimeters. So whatever is there in 40,000 meters, it will become 40 meters, which is a realistic scale. Okay, to do that, we have to first set up a case and only then we can do that. Okay, to set up a case, what I'm going to do is first I will open my WSL. I will navigate to my OpenFOAM location. So this is where your run location usually will be. So you can navigate by cd $foam_run, but I have different command for that, so I use this. This is the place where you will have your tutorials folder. Inside this, I have a folder called YouTube. Here I am going to make a new directory, so you can follow from this step. When you are in your location where you want to set up your case, you can follow this. So I am making a directory named aircraft. So I am entering that location. Okay, after entering that location, we are going to copy a default tutorial case, which is cp-r $foam underscore tutorials. So under that we have incompressible folder. Under incompressible we have simple foam. Under simple foam we are going to take the famous motorbike case as reference and we are going to paste it here. Do not forget this last dot, it is very essential. It means that we are going to paste it in this specific directory. Okay, now if you see we have the motorbike case here, but we can rename it however we want. Okay, I have this folder here and what I'm going to do is I'm going to rename it to aircraft. Okay, so in this we have the default files. We do not need the all run file, so I'll delete it. In the system we have so much of files which are not actually necessary for this demonstration, or any case in most simulations you do not need all of these files. So I will just change it to system.original and create a new folder called system, where we will copy only the essential files, namely BlockMesh dict, control dict, decomposePar dict, the FE scheme, FE solution, mesh quality dict, snappyHexMesh dict, and surface feature extract dict. I will just copy these files, go to system and paste it here. And we have to rename this file from decomposePar.6 to decomposePar.dict. Give s. Okay. Okay. We have all of these files. Now we are supposed to create a new folder called try surface. Inside this constant folder, this is the place where we will be pasting our new STL. But before that, as I said, we have to convert the STL from large scale to small scale. Okay, to do that we will paste the STL file here. Okay, and just go to Google. There is a CFD direct post where you can find the command to convert the scale. There are many commands, like you can use this command, or there is one more command with this. So I personally prefer to use this command, but if you want you can also use this command. So I'll copy this, go to my terminal. So we have to go inside this aircraft. We have the aircraft ASCII.stl here. Okay, so I'll go here, paste the command. Now we are supposed to change this, like surface convert, and then the input file's name, which is aircraft ASCII.stl, and in the out file we are going to give the name, which is aircraft.stl. So this is the output file name, and if you see the hyphen clean, let it be there, hyphen scale, and we are scaling it down by a factor of 1000. I'll just hit enter and it will convert it. Okay, if we had used a binary file, this would not happen. So this is the method to check whether your case is in ASCII or binary by default. So you can go here and see we have the aircraft.stl file. Now you can judge that this is a large file, this is a small file, so this is obviously smaller in scale. So I'll copy this, go to constant, inside try surface I will paste this aircraft.stl file. To verify I will delete this, I'll go to open, and I will load this exact file from try surface and verify if what we have done is right. Yes, it is right. So we are using 40, 10, which is in realistic scale for X, Y, and Z. Okay, now this is done, but how to do snappy hex mesh? We have the geometry. Okay, so we are first bound to create a block mesh dict, which will act as the background mesh. Okay, so to do the BlockMesh did, we will first generate whatever is there by default. Okay, I will do touch para.foam. What this will do is it will create a paraview file. Okay, now I will create a block mesh. So this will in a way create default block mesh which is already there, but it is throwing error because there are certain functions in control deck which we just deleted, or we do not need any of these because these functions exist in the original system.original file. These are streamlines, profiling, and cutting plane, all these. We do not have these in the system. So it is safe to remove those things from the control deck. Okay, now I will run the block mesh. It has created the block mesh. Okay, I will close this paraview and I will open new paraview file. Once I opened it, I will go to wireframe mode. Now this is an iterative process of creating the background mesh. I am going to go to try surface, click on OK, click apply. As you can see, this is totally out of the background mesh, while this is actually supposed to be inside. So what I'll go here and turn on data access grid, so we will know what is the actual size. So I'm going to do one thing. Go to system, open the BlockMesh dict. Now we are going to change the BlockMesh dict's parameter so that we are having a proper mesh. The scale I will change it to 10, so whatever is there as default mesh, we are going to scale it by a factor of 10. I'll run BlockMesh again, go to paraview and refresh it. So as you can see, now we have a very big mesh. Okay, but it is not uniform, like it is not symmetric. So I am just going to change it in a way that it is symmetric. So we do not need up to 150 here, 100 is enough on x-axis, as you can see. So I'm just going to change this from 15 to probably 11 because I think 11 would be more suitable. I will just save this, go here to my terminal, run BlockMesh again, go here and refresh. As you can see, now it is more symmetric, but again we have to change the dimensions on the y-axis. It is from -40 to +40, which in this case is lowered by a factor of 10. So instead of -4, we can have -5, which will be 50 in that location. Okay, I will save this and run it again. I will refresh it here. As you can see, the Y is now decently big, but I think it is not yet sufficient. So I will probably go up to 7. But if you have a specific dimension to work with, then please go with that, because whatever I'm doing in this tutorial is not to run the case, but instead just to demonstrate how to work with snappyHexMesh. So you just follow the proper physics and maintain the distance between walls and the geometry properly. Now I am going to change the z-axis. So this is not enough for the flow to develop. So I'm probably going to change this as well. As you can see, this is the 0 and this is 80. So I have to change these 4 parameters for the z. Instead of 8, I'm probably going to take 12 and see how this goes. So this is all trial and error method. Okay, now we have some decent distance from the nose. On the trailing edge also, we are bound to make a longer area of fluid domain. So I will go here and instead of 0, we are going to have something around -15. Again, this is just an assumption, just to see how well it goes. If it is not sufficient, we will again change it. See, now this is okay. It's not too big, it's just okay. But if you see in the z-axis, the number of divisions is not sufficient. So I will change it in this. Instead of 8, we will probably go around 15. And even in y, instead of 8 will go for 10. I will change the block mesh. Now this is okay-ish, okay, but for such a small geometry we must have the background mesh more refined. So what I'm going to do is I'm going to scale up everything. This will be 50 divisions, this will be 30 divisions, this will also probably be somewhere around 50 divisions. I will save this, run the block mesh again and refresh it. Now you can see we have pretty coarse mesh. I mean, it's not too coarse, but it's a good decent mesh for the background. If you want to go further down, it's okay, but I think it is not essential to go more refiner on the boundary walls, because our flow domain is here, which we will take care of while doing the snappy hex mesh. But there is a problem again. I will check out the internal mesh and see what is the inlet. By default, if you see, this was the inlet, and this was the outlet, and everything else is also collapsed. Like if you see, the upper wall and lower wall are now the front and back. So this is, I mean, the inlet and outlet. So this is not a good way, right? So what we are going to do is we are going to rename everything. If you see, if I select the lower wall, this is the actual outlet. So what I'm going to do is go to the block mesh dict, copy the coordinates of lower wall, and paste that in the outlet, and comment what was already there. And we do not need the lower wall now because it is not right. Okay, now we are going to run block mesh again and see. Now we will just select outlet. Now this is the outlet. Okay, instead of inlet we have the upper wall, or okay, we also deselected the upper wall, which is here. So I will copy the upper wall, go to the inlet, paste it here, comment what was there already, run the block mesh again. Now you can go here and refresh with inlet and outlet. As you can see, we got the inlet, which is right. Yes, this is the inlet. Now we have to change other things also, like we can set the front and back now. So if you see, the front and back is now the top and bottom. Okay, so what I'm going to do is I'm going to comment front and back, copy this second one, and try if it is the upper wall, which I think it is, and the first one, it might be the lower wall. If it is the exact opposite, we can still change it. So every time before running it, just make sure that you are saving this block mesh file. So run block mesh and go here, click on refresh, and if you select lower wall, it is in upper actually, and if you go to upper wall, it is in lower. So what we have to do is just invert this. You don't even have to change these two, you can even change the name. So this is upper wall and this is lower wall. I'll save this, run block mesh again, and see what is there. So if you do not want to do all of these one by one, then you can create your own block mesh from scratch. That's fine too, instead of changing every parameter. So I'm going to check the lower wall. Yes, it is the lower wall. If I check upper wall, yes, we have it. So now we have inlet, outlet, lower wall, and upper wall done right. We just have the front and back, which in this case doesn't make sense for front and back, but yeah, doesn't hurt to just have a name. Okay, so I will keep it front and back. We do not have anything here. So what is actually the front and back? It was the inlet and outlet previously. So I will copy that, remove the comments, and I will replace this with the inlet, the previous inlet, and the second thing was previous outlet. Save the file, run block mesh, refresh, Now you can see we have front and back. When I select front and back, I will just check it. So for inlet, yes, we have inlet. For outlet, yes, we have outlet. For lower and upper wall, yes, we have them. And for front and back, yes, we have them. And if you see group wall, only one is in the group wall, which doesn't matter actually. So I will close this. We have the background mesh done. Okay, the next step is to set up surface feature extract. So whatever STL we have, it is converted to OpenFOAM understandable language by this feature. Okay, so I'm going to change this like from surface feature extract. In this by default it is motorbike.obj, but we have aircraft.stl already loaded. So I will change the file name and I can go to the terminal, make sure that you are in the working directory where 0 constant and system is there. Now you can type surface feature extract and hit enter. So you will see this end message, which is good. You can also ensure whether you have the extended feature edge mesh folder as well as .emesh inside try surface. So the next step is you can go to system and we can set up the snappyHexMesh dict. So this is the most important file. Here let everything be true. If you do not want to add layers, you can change it to false, but let us keep it true. Here we are going to set up the motorbike.obj to aircraft.stl and the name, this is the name which we will be using to represent this body. Now we have to set up the refinement box also. So how refinement box works is, let's say we have a mesh or box like this. So to define this box, what we can do is we'll just define this point and this point, which is opposite diagonal, where this is termed as the minimum and this is termed as the maximum. So these two will be defined, so it will create a box within this bound. So this is known as the refinement box. This is what we are going to set up. So how do we actually know how to keep the refinement box? I will open this paraview file which already has the background mesh and I will change it to wireframe mode. I will now import the aircraft.stl file here. Okay, the refinement will happen within the section where we actually need the refinement near the walls. Okay, so to do that we will define the points based on data access grid. First we have to set up the minimum. If you see, the z-axis goes from negative to positive from left to right. Here x goes from 0 to positive, which means the negative is on this side, and even if you take y, it is minimum on this side. So the box is probably going to go from this point to the opposite side of that point. So I hope you can understand that. We are going to set up the minimum point now. On the z-axis it can be -20, on y-axis it can be -20 again. So 20 comma 20 for y comma z will something look like this, but I think we can even take -10 for y. So let us define something x comma y will be -10 and z will be -20 in the minimum. So we do not know the x as of now. Just going to set up this, y will be -10 and z will be -20. Now we can see what is the x. So for x I would say we can even go with 0 because 0 lies here and that is okayish. So I will take 0. Now we have to set up the maximum point. So if this is the minimum, then the direct opposite diagonal on the other face, opposite face, would be somewhere around here. So the x, in my opinion, it can be around, if 0 is here, then we can go something like 60 or minus 7, somewhere around 60 is fine. Let's just see. So this will be 60, positive 60, and the y and z we have to choose. For y-axis we can take the exact positive of this, like we took minus 10, so now we can either take positive 10, but it is interfering here, so we will go for something around 30. So this can be 30, and for the z-axis we will take 60. Okay, so I will take 60. Now just make sure that every point in the maximum is greater than what is defined in the minimum. Otherwise something is wrong with your points. So every point in maximum should be greater than minimum correspondingly, like x, y and z. I will save up to this. Now we can go to the next things. If you see in the castellated mesh controls, it has maximum local cells, maximum global cells and everything. If you want to adjust these parameters, you can read these commands and understand what the parameter actually says, and you can edit it as you need it. But I'm not going to do, since this is only for demonstration purpose. Here I'm going to change this to aircraft. And you just know that initially we have a factor of about 6, but just for trial we are going to change this to 2, because we just need a rough coarse mesh, then we can refine it as needed. And same here, initially we have 5,6, but for demonstration or to see, we are just going to keep it as 2,3, and patch info will be wall. Now this is the same name which we defined there, where here. So this and this should match. Okay, and in the patch info the type is wall, the group will be aircraft group, but you can also name it aircraft, this doesn't matter. And for resolve feature angle, lesser the angle, greater the resolution, but I'm just going to leave it as default since this is tutorial case. But if you want to refine, you can go down on the values. There is one thing which you have to know. In this resolve feature angle, lesser the value, more refinement. But in surface feature extract, the greater the value, more the refinement. If you click, if you set 180 here, which is the maximum, it will be more refined. But in this case, you can go less than 30, also around 10 or 5, which will have more refinement. So it is opposite in nature. And for refinement regions, let this be around, okay, let this be around 2, but we will remember that this was by default 4. And now location and mesh is very important. Whenever there is a geometry like this and there is a block mesh around it, if you choose a point inside the STL file, then the mesh will be created within the bounds of the geometry. But if you choose a point outside the STL file but inside the block mesh, then inside of the mesh, inside of the geometry, it will be a cavity, and the mesh will be created within the block mesh. So in cases of external aerodynamics, you have to choose a point outside the geometry but inside block mesh. But in case of pipe flows, we have to take a point inside the pipe so that the mesh is inside the pipe. So that is what the location and mesh actually defines. In our case, we can choose anywhere around here inside, so that's not a problem. In x-axis, let's take 0. In y-axis, we can again take 0. In z-axis, we can take minus 40, so that will lie somewhere around here. So in our case, it is 0 comma 0 comma 40, not comma, just x, y and z. Save up to this. Now to make it more refined, you can read these commands and see what exactly these values do and refine it for your case, but I'm going to leave it as default. And in case of add layers, you can change these to aircraft. But if you are doing something like a motorbike case or car, then you might also have to choose lower wall, because lower wall has impact over the flow domain. We have to see what is the shear force in case of a car or something like that. But in this case I do not need layers there, so I'm just going to choose aircraft and let the number of layers be 2. If you want more layers you can choose that. If you want to calculate the final layer thickness and have it here, so everything is in SI unit, which is in meters, so you have to remember that. And you can choose the minimum thickness also, number of layers, expansion ratio, everything can be controlled here. So you can read these commands and know what these things do. But for now let us leave it as default and see what this generates. I mean, this snappy hex mesh will generate a coarse mesh. It will not be sufficient, but we are going to do. But before that, snappy hex mesh takes a lot of time to generate mesh. So I generally prefer to do a decompose even for meshing. Decompose can be used not just for running a case, it can be used even for meshing. So I'm going to change this to Scotch method, and I have 8 processors. If you do not know how many processors you have, you can open your task manager, go to the second bar, choose CPU. Here you will see cores. You have to choose 8 here. In case of commercial software like ANSYS Fluent, you can use even the logical processors, but in case of OpenFOAM you can only use the physical cores. So it is 8 in my case. That can be typed here and use the method Scotch. I will save this. Now I can go here and do the check mesh. So the mesh we already have is only based on BlockMesh. Okay, so we are going to create snappy hex mesh on top of this. To do that, first we have to decompose par. So this will decompose the available mesh, which is BlockMesh. On top of this, we are going to run snappy hex mesh in parallel. So it is mp run hyphen np, which is number of processes, 8 snappy hex mesh, and always do overwrite when you run snappyHexMesh. Otherwise, it will create time steps for each refinement. And then finally mention parallel. When you hit this, it will show any errors if it is there, but probably I hope I did not make any mistake. So let this run and I'll get back to you once this is over. Now the meshing is done. You can see end finalizing parallel run. Once this is over, you have to reconstruct the mesh into the constant folder where polymesh is there. Now polymesh contains only the block mesh. So you have to reconstruct par mesh into the constant. So you are going to do reconstruct par mesh space hyphen constant, hit enter. Now this will reconstruct the entire mesh. Now you can safely remove all the processor files. So now we have a clean case. Now to view the mesh, you can close the existing paraview, go to your folder and open the paraview file. Now as you can see, we have the mesh on the aircraft also. To view that, you can click on this, click on apply, maybe change this to surface with edges, zoom in. But as you can see, it is not very good, right? I did not capture most of the features at all because we kept the refinement levels to low. Okay, to do more refinement, we are going to start a refinement process which will refine this. Okay, to replace the polymesh folder with blockmesh again, I will do blockmesh. Now we are going to go to the surface feature extract and change this to 180, save the file and again run surface feature extract. So now this will capture more of the details from the model and store it. Now we can go to the snappy hex mesh bit and change certain parameters which might be helpful. I'm not going to go into everything, but only those things which are basically needed. Like this can even be 7 or 8 for case like aircraft. Let me keep it 8, and in this case it can even again go up to 7 or 8. So this is like minimum and maximum values. I'll keep it as 7 and 8. This resolve feature angle, let me not change this because I do not know how this will affect finally, so let this be default, but if you want to do the trials you can. And for refinement box, let this be 4, and the location in mesh is obviously not going to change. Okay. Okay, I will even change this to 5. In snap controls you can also tweak these parameters to get a finer mesh, but I'm not going to do. Even in layers I'm going to choose 6 layers, and I'm just going to leave everything else as default. Save this file, but if you want to do more refinement on the surface, you can first choose these parameters. If it is still not sufficient, then you can again do it. Okay, now if you see the block mesh again, the polymesh again has only details of block mesh, so I'm going to decompose that block mesh. If you did not run the BlockMesh command again, it will have the previous snappyHexMesh, which is not a good thing to do. So you just need to have the BlockMesh and then run mp run with snappyHexMesh parallel again. This will take definitely more time than what was necessary previously. So I will start this, and once it is over, I will get back to you. While the mesh was running, it actually gave me an error that my computer could not handle that much refinement. So I actually went back to snappyHexMesh Direct and changed these values to whatever we put in the comments to the default values so that it can handle the mesh. It was not sufficient to have 8 processes alone to do this mesh. So I changed it back. Now the meshing is running, and I hope it will finish without any errors. Now the meshing is actually done, so I will do the reconstruct par mesh. So this will essentially reconstruct all the mesh from all the processes and put it inside a constant under polymesh folder. So now I can remove all the processes folder because it will take a lot of space, and we have this. Okay, now I will close this and open the paraview file again. So now we have the bound box here. I will just choose aircraft so we can see how refined it is. Now you can see it is much better than what we had already. Still it is not sufficient, I would say, but this is definitely much better than what we had with less refinement. Like as you can see, it is capturing more details. So if you can go further down, tweak certain parameters and get perfect mesh, then it is a great thing. Okay, for demonstration purpose I'm not doing any of those, but depending on your geometry you can do those things. Now I will show you the layers which was created by add layers function, which can be seen by creating a clipping plane. So you can see this is the refinement box which we created, and this is the geometry. We are having only cavity, and if you go here we can see 6 layers. Okay, so this is what was able to create by the add layers function. So we have this. Similarly, we can also see what is there in the frontal view. Around this place, and go to the Z plane and go to the surface with edges. As you can see, this is a decent mesh. Okay, it is almost symmetric. If you do perfect calculations and set the bound box, then it will be more perfect. If you want to see uh, the mesh along with the plane, then you can actually load the case again. like this and choose only the aircraft. Then either you can view like this, or you can go to surface with edges and see the mesh here as well. Like you can go to slice to show plane and physically move this, click on apply. Now you can see it much better. Okay, now we have created the mesh. Now the inlet outlet is also fine, but before actually running the case you have to change certain things, right? So let us take example of U file. Here you can just change from motorbike group to aircraft, because that is what we created in the snappyHexMesh date. Like if you remember, initially this place was motorbike group, we changed it to aircraft, so you have to give the same name here. And similarly you also have to change in every other file in the zero directory. Like this has to be aircraft as well. You can change this to every file in the zero folder, and you can set whatever velocity you intend to keep and whatever turbulence model you want to do. Everything else remains the same for what you do with an existing mesh. But this is the process for creating mesh with snappyHexMesh. I hope this was useful. If you have any specific doubts related to this tutorial, you can feel free to comment in my video. If you have any specific requirement of anything related to OpenFOAM, please drop down in the comments and I will try to make a video on that. If you like the video, please drop a like, consider subscribing to my channel. See you in the next video. Thank you.